Hi everybody. A bit of a change of topic here. I'm Josh. I'm a doctoral student here at MIT in physics. And today I'm going to be talking about a proof of concept that we did, which is using Julia to build machine learning powered surrogate models of particle accelerators. So before I get into kind of the physics and the context of this project, I want to give away the punchline. Basically, when we're designing these sorts of like particle accelerators and this machinery for this sort of thing, we have to run these very computationally heavy simulations that take a long time. And the idea is, can we build machine learning based replacements of that are good approximations for the sorts of things that we want to accomplish? These surrogate models are useful for a whole hearth of reasons, one of which being the optimization of the design of the kind of particle accelerator that you're building, and that's what I'm going to talk about today. And the surrogates and the flux packages were awesome for this. This is really an exploratory project to explore Julia as a language for me, so yeah. So for a bit of context, I'm going to talk about the experiment that I work on, which is called ISIDAR. So I am a particle physicist, and my favorite kind of particle is called the neutrino. Neutrinos are very bizarre. They have a lot of behaviors that we don't really understand, as we do many of the other particles in the standard model. In fact, there's a lot of dissonance with neutrino experiments worldwide. They get numbers that don't match up, and a nice resolution to this sort of disagreement is the introduction of a new particle that hasn't been seen yet called the sterile neutrino. ISIDAR is meant to sort of once and for all either rule out or rule in the existence of the sterile neutrino. And to do that, we had to have like a host of technical innovations that get us right to the sweet spot of finding the sterile neutrino. And one of those is the development of a kind of accelerator called an RFQ, which I'll talk about on the next slide. Here sort of you can see sort of schematically what's happening in ISIDAR. This is being planned to be installed in an abandoned mine in South Korea. And I have resources at the end if you want to learn more about ISIDAR. So the component that's necessary for ISIDAR's design is called a radio frequency quadrupole. So hopefully a majority of us in the room have taken like Physics 101. And so we know that when we have an electromagnetic field and we put something that's charged in the electromagnetic field, you experience a force. And you can design these sorts of electromagnetic fields in a way so that you're like focusing a beam of charged particles, and you can like sort of accelerate those to the energy that you need to run whatever kind of experiment that you need. And that's sort of shown schematically, like in the bottom right figure. The little gray arrows are the electric fields inside the cavity of the RFQ. And then the green and the red arrows kind of show like the focusing and the defocusing effect that you see as your beam traverses the accelerator. A little more technically, we have a bunch of wiggles or like RFQ cells inside this RFQ, and that has the effect of like kind of alternatingly focusing in the X and the Y directions as your beam sort of propagates through your detector. Because of ISIDAR's technical specifications, we run into a bunch of nonlinear effects, which make simulating and sort of like solving these differential equations as like the particles propagate through the accelerator very difficult. The biggest one being space charge. And that really blows up the like computational runtime of our simulations and kind of puts existing software packages to their limit. I think to generate the 200,000 samples that we used in this study, it took over a month on like the high fidelity simulations. And so the idea is that we want to replace that with like an approximator. So these surrogate models are useful for a variety of reasons. There are a couple that have been explored previously, one being uncertainty quantification. So you can approximate using these kinds of models the errors that you'll see in your experiment when you eventually get the thing up and running. You can use it as a real-time feedback tool. So when you're actually operating the machine, you can turn a knob and instantaneously see how the output or your beam quality is going to look. And then you can also use it in place as like an acquisition function for design optimization. And that's what we did, which is you can use this neural network in place of the higher fidelity simulations to run like a multi-objective optimization on all of the design tweaks that you can make to your RFQ. Great. So for this study, we had just north of 200,000 simulated samples. there were 14 what we call design variables, which are ways that we parameterize like the different features of an RFQ. And those are kind of listed by their like code names, I guess, in the bottom right. There were 6 objective variables or responses. These objective variables are very closely related to like the quality of the beam that you see on the other side of the accelerator. So like an example being transmission, which is exactly what you think it is like how much of your beam actually makes it through the accelerator. There were 2 objectives that in previous work was really hard to pin down, and that's objectives 5 and 6, which are called admittances. Admittance is like a figure of merit in my field for like beam quality. And the problem is that like we didn't have any way to resolve the asymmetries in the 2 transverse directions of the beam, the 2 X and Y directions. And so to do that, we extended our data set with one extra feature, which was really nice because we could link Julia to like a pre-existing Python script that like ran this thing for us. And that's how we got the number of RFQ cells or the number of wiggles as our 15th feature, which helped us a lot. We made some appropriate transforms on the data to make sure that we were showing our neural nets like physically feasible samples and that sort of thing. And then whichever neural net won from our hyperparameter scans was the one that we plugged into this design optimization at the end. And so here on these 2 tables on the right column, you sort of see the benchmarks for the % errors from the best performing neural net from like a previous paper that we had done on this. And then RFQNet1 and RFQNet2 are the 2 neural nets that we had trained in this study. The only real difference between RFQNet1 and RFQNet2 is that we limited the data that we showed the neural net in the second case because when your beam transmission gets too low, it turns out that like your samples basically lose physicality. So they're like no longer physically realistic. And that tended to throw off the performance of the models. And RFQNet2 kind of blew it out of the water. The % errors on that neural net are a third of what we were seeing previously, which is really exciting. And then the last thing that we did is we plugged in RFQNet2 into like the surrogates package, and we ran a multi-objective optimization on like sort of the technical specs of ISODAR, namely you want your transmission to be as high as possible, you want your beam quality to be as high as possible, and you also want to match the energy that we need to like run our experiments. And you can sort of see the optimal design that we sort of converged on as like the orange star superimposed on like the rest of the Pareto front, which is blue. This like had like a pretty exceptionally low emittance, which is like really nice. It means our beam is really good quality, and a transmission of above 95%, which is also really awesome. So yeah, I mean, Julia was great for this. And when you're careful about the data that you show these kinds of models, especially when it's like a physics problem, that really seemed to help things. And in the future, we'd like to explore more sophisticated neural network architectures to handle this sort of problem. So here are my references, and then if you want to learn more about ISODAR, there's a YouTube video that someone in my group had posted that sort of runs through it. So thank you very much.